Hey, well, good afternoon, everybody. Welcome to the Geospatial Forum. We have a really special event today. I'm really excited to start a new tradition of showcasing doctoral students and their research at least once a year. Maybe we can do it more often. And today we have four doctoral students in and affiliated with the Center for Geospatial Analytics who will be presenting 7-minute lightning talks about their work, followed by 3 minutes of questions. And then so we'll have some time maybe for discussion at the very end, or we can end the day early. Our speakers are Kellyn, Montgomery, and we have Umesh Gupta, and Jason Matney, and Devin Gatos. And two of the students are first-year students, Umesh and Kellyn. So special kudos to you for your courage getting up here, presenting your very, very preliminary work. Great. Anybody have any questions? John, where's John? Right here. Has agreed to stand up at 7 minutes. There are some side bets that Umesh would not finish.
Yes.
But
talk to Rohit.
In a real lightning talk for a competition, if you go 1 second over, you're disqualified. So you've got to stay. We'll use this as practice to stay on time.
I'm getting out my conclusion slides.
Well, thanks again, everybody, for coming out. I know it's a gorgeous day. We'll try to finish a little before 5, before 4:30, and everyone can get on with their day. But it's really exciting to do this. All right, Kellyn.
Okay, yes, again, thank you guys for coming to support us Ph.D. students today and giving us the opportunity to share our research and our ideas. So about 6 years ago, I was working as a GIS analyst, but looking for a career change into something that I thought would have more of a positive impact. So I quit my job and I moved to Goldsboro, North Carolina to work on a farm at the Center for Environmental Farming Systems. And I started to learn about the many challenges of agriculture, both economic and environmental. And I started to realize, actually, I could do more good with my GIS skills. They're really well suited for addressing the problems there. So that brings me here to where I am today. I'm using unmanned aerial systems to make 3D models of crop canopies. But since these surfaces are pretty new, I'm looking at borrowing techniques from terrain surface model analysis to see if they could be applied for agriculture. So as the world's population continues to increase, we'll continue to face issues with food security. There are some projections that say we need to double our production in order to meet demand. But at the same time, agriculture can be have a notoriously bad impact on the environment. Poor practices can result in soil loss, water pollution, and loss of biodiversity. So at the same time, we have this challenge with production and conservation that we need to face at the same time. So precision agriculture has really emerged as the most promising strategy for addressing both of these challenges. The idea is to use spatial technology to identify variability within a field so that a farmer can apply precise management just to those areas to increase yields, but also limit the use of inputs. Spectral remote sensing is one of the primary tools used. We can see things like crop greenness, stress, soil moisture, and in particular, remote sensing with unmanned aerial systems is a really excellent tool because it's relatively inexpensive, they're really easy to use, and they're really versatile. So you can monitor whatever, whenever in the field. Oh, one other point I want to make about UAS is that we don't talk about this very often, but the fact that the farmers can use the UAS directly, it keeps more of the decision-making power on the farm and therefore with people that have the most interest in protecting their land. So in addition to multispectral data, which can require pretty expensive sensors, we can use visible band imagery from UAS to create 3D point clouds of vegetation. So with these point clouds, we can get a detailed, complex canopy surface model. And when we have this geometry of vegetation, we can start to ask questions about how the shape of the crop varies and what that variability might relate to in terms of stress or health of the crop. And the way I like to think of this is if a farmer is driving by a field doing some sort of visual inspection, what are the visual clues that they're using to do that assessment? So can we automate that process to make it more efficient, especially in the case of really large 1,000-acre farms? And what's more, is there some 3D information that we can extract quantitatively that would be lost just through visual inspection alone? But these surface models come with a lot of challenges. Unlike terrain surface models, they're really rugged and complex. And we might find that the structure for motion algorithm used to make these surfaces works better with certain types of vegetation than others. So here we have grain sorghum, which is a grass species, compared to broadleaf crops like soybeans and tobacco. So each of these plants has very different architecture. And we really don't know how well the algorithm does at pinpointing the same point on the same leaf on the same plant across multiple images, which is really required in order to make an accurate 3D model of canopy. So this is one thing that I hope to address in my research, to assess how accurate these canopy models are, but then also how much detail do we really need in order to extract meaningful information. So thankfully, in terms of analysis, there's a lot of work that's been done on analyzing other types of surfaces, especially in geomorphology. So I'm borrowing techniques to create some sort of geometric signature of plant characteristics, like uniformity, roughness, or change over time. So for example, I'm using relief ratio in sorghum to detect edges or stark changes in crop height to detect gaps within a canopy. I'm using geomorphons in tobacco. It's proven useful for mapping different parts of the canopy. And then in soybeans, I'm using core and envelope, or essentially a minimum and maximum surface, to understand how the crop changes over a growing season. But ultimately, I'm interested in whole farm systems modeling. So these canopy surface models can be combined with other site-specific parameters about soils or topography, and also economic information to help a farmer understand the best use of their land. This type of multi-dimensional analysis can help a farmer balance the trade-offs between production and conservation so that they can be the best stewards of their land possible. Thank you. How'd I do on time?
6 minutes.
Oh, sure.
Yes, we are. Yes. There's 3 minutes for questions.
Yeah, Nick.
So it seems like one of the major pieces of your work is time series. So you're taking repeated measurements throughout the growing season.
Mm-hmm.
How do you quantify change in a meaningful way between surfaces? I know you explained the complexity of going from image to image, but how do you actually know what is real change and what is difference in algorithm or data collection?
Right. Well, I think that there are a couple of things going on with that question. One is you have to figure out the right time step for measurements. So ideally you would start very early in the growing season, and then maybe once every couple of weeks at some time step where you can see some significant change, so that you don't have those same issues, those issues of being able to differentiate what's noise and what's actual change. And there are also some challenges when you're looking at a time series. You have to make sure that everything is starting from the same baseline. So you can have issues with distortion in UIS data. So you have to either know that you have really great ground control points, and so everything's been georeferenced correctly, or do some sort of post-processing to make sure that things line up correctly so you can detect change. And I'm still exploring how I'd figure that out quantitatively, what's been changing. But one idea we've been toying with is the idea of monitoring a field that has some sort of ideal growth, like a very ideal situation, and then kind of using that as the model to compare to. That if you see some deviations from this expected growth curve, then maybe there's something going on to investigate. Yeah, Jason.
So I briefly interned with this company called Growers.
Yeah, I've heard of
in
them.
North Carolina. And so what they're precision agriculture company, and what they're mostly focused on is identifying prescriptions that can optimize yield.
Yeah.
Do those prescriptions factor into your research with the aerial imagery? Is aerial imagery or not?
So I think those prescriptions are usually for inputs, right? Variable rate, fertilizer, or pesticides. So I guess I don't see a connection directly. However, it's kind of using the same technology that is giving me a wealth of data to work with. So we have a lot of historical data to look at for how those variable rates have affected crop heights in the past or crop yields in the past. So it could be used as kind of an input for a model. Yeah.
So do you think your algorithm is going to have to change based on the time period of the crop, like as it's growing and then it changes and once it senesces and starts to die back and the leaves fall off, do you think you have to change your algorithm?
Well, I think that one thing I've learned is that it's really too late at that point. If it's senescing, that's not the time of development that I'm targeting. It would need to be earlier in the season. But I guess you would have to understand what you would need to expect in the field. Like what growth behavior do you expect at whatever type point in the growing season? And that's what you would base your measurements on. Yes.
What's the the best resolution you're getting for UAS? Leaf.
Right, yeah. So when I first started doing this, I really wanted to know what we could see even just in an ortho image, if you could see some damage on a leaf. So I've experimented with almost 1 centimeter resolution. So that's flying at 30 meters, which this is one of the questions I have, is what's the, I guess, maximum resolution we can use and still get meaningful information, because I think 1 centimeter is it really introducing more noise than real meaningful information. So I've seen maybe 5 centimeters. It's kind of where I'm aiming now. Yeah, would depend on the plant for sure.
Thanks, Kellyn.
Okay, thank you.
Are they same?
I think I might just plug me in. Yeah.
Okay, and I forgot to mention that Kellyn is advised by Doctoral, and Umesh is co-advised by Dr. Raju Vatsabai.
Well, thanks everyone for making your presence here, giving your time. I have a script actually because I want to be right on time. I have a bunch of people who are going to time me actually and hint me also. So the title of my talk is motivated from the data science challenge. If you already know Kaggle data science competition. So we have a very new competition introduced called Deep Globe Satellite Image Understanding Challenge. So basically it's a public competition for segmentation, detection and classification tasks on satellite images. AI and deep learning was already a big buzz with the computing and data handling innovation happening around, and many important fields including geospatial saw an immediate advantage. Computer vision and machine learning community is today motivated to work on a larger problem in remote sensing and is already known as, or is widely known as photogrammetric computer vision or earth vision formally for understanding Earth. We all observed that satellite imagery. This is a UAV image, and I have tons of images which is coming from a company in Australia. We all observed the UAV and satellite imagery is a rich and structured source of information. Yet it is less investigated than everyday images by computer vision researchers. However, bridging modern computer vision with remote sensing data analysis has a critical impact to the way we understand our environment and lead to major breakthroughs including global urban planning or climate change research. Generally, the problem involves finding relatively small targets, vehicles, ship, electricity, generators, windmills, and other infrastructures in a large scene dominated by clutter. In the past few years, or in the past 5 years, many useful applications of AI have emerged in the domain of remote sensing, and it's continuously growing. But where are we now? Where are we moving? We are doing great in both applications and AI technology research, and have moved beyond the simple classification, detection, and segmentation tasks in different many image types. The money spent and jobs served are higher than any other field. So this is 9.1 billion is already money spent last year on AI research. And we have planned to spend much more money, and we have 100,000 jobs already posted in AI. So if anyone of you wants to get into this field, it's the right time. But this is certainly not a joke, or it's certainly not a very simple implementation. AI is a serious business today. Simple AI deployment is no more cool. New techniques and methods are introduced each day. AI is simple, but if it is to be done on the remote sensing data, it's really a hard field of work, especially when you're dealing with high resolution, complex imagery. AI and remote sensing is something that I want to highlight today about. Object detection and land cover classification seem to have been the most researched and commercialized applications of deep learning in remote sensing. But there are a number of other areas that have also been benefited, like data fusion, 3D reconstruction, and image co-registration. Cool. The ever-broadening use of deep learning in remote sensing is due to recent trends and new company and their products. Easy to use cloud infrastructure with GPUs, the development and increased adoption of easy to use machine learning tools and open source frameworks, an expanding ecosystem of different label training data sets and open label data sets. Well, I'm taking this opportunity also to introduce you to all my PhD research goal and work. We are calling it as Project Open Sky. Sky also because it is all aerial and remote sensing data set that we are going to work on. It's called Satellite Scene Knowledge with AI. We are going to target all the remote sensing and aerial data set. Taking motivation from the literature and products in research, we want to develop new technique and a workflow around modern remote sensing challenges. Haven't yet specifically decided what different questions we want to answer, but we are exploring recent and advanced techniques that can be tweaked and used on large computer vision problems like remote sensing. Very high resolution images are available today. It gives potential research opportunities for Open Sky framework to solve many different challenges and serves as an AI testbed. Open Sky will be using different ways to enhance training data through simulation and transfer learning, but we still need a reasonable data to start at a starting point. I'm still to plan my strategy and do some hyperparameter tuning, but I'm sure it would work on this kind of new data sets. When I say large, I really mean a large scale here. Something like what Oak Ridge National Lab tries to achieve. Looks simple but truly challenging. There are three main work that I want to highlight today, which I'm planning to immediately use in building Open Sky. This is a work by Oak Ridge, very recently published. Although the re-emerged interest in convolutional neural nets lead to significant success, especially in the natural images from computer vision applications. Earlier, the CNNs couldn't directly be used on the remote sensing images, but we have widely known CNNs such as VGG nets and image nets to be used for the remote sensing imageries. However, the extracting building from remote sensing images from needs a semantic segmentation and can be possible using standard CNNs, but there are a couple of challenges. So what we see here is the building extraction for the Pennsylvania state, and it's a first large-scale object detection model ever published. Done on such a large scale. I think they have done for the whole US, contiguous United States, with the average processing time less than a minute for 56 kilometers square. These are unit segmentation. This is the version of unit segmentation for satellite imagery. It does a semantic segmentation for satellite imagery. With a significant progress made in deep learning and CV, we can achieve a really predicted segmented image like this. So what you see in the first column is the true satellite image. The second one is the true mask, but the third column is the predicted one. So what you see there is better than the true mask that we have. So we are reaching to 100% success in any a work like this. And UNet is a very famous mod architecture, has received around 5,000 citations in a couple of years. I'm also excited because U is what my initial. The GAN is my favorite network here. I'm showing, I think many of my folks already know about GANs, but for someone who is introducing first time to GANs, it's a competitive architecture. It's an adversarial game between two networks of fooling each other and generating new data sets. So this is very recent work using GANs to generate the realistic SAR images. What we see here is the actual SAR image, which is denoised using this architecture, and then it is colorized using again in the same model. So we have the photorealistic SAR GAN image, which is better than the satellite image what you see. And I'm learning hard in remote sensing. It is not easy for me, but yeah, I think all sounds so cool. The idea is to show where are we in terms of adapting fun technologies like AI, and what I'll be trying to use in the Open Sky framework. Thank you. I have an awesome committee. I think I'll achieve what I want to achieve in my PhD research work. That's all. I saw John waving me, but I couldn't. And I have to give lunch to my folks because we bet on the time, and I think I was already beyond 7 minutes. So I won or you won? You won? Sorry. But okay, anyway.
Questions are you addressing in any way of the what's being done with AI modification of images to basically modify them so there's incorrect information?
You're talking about semantic labeling, or?
No, I just read an article.
Okay.
That basically, especially for Intel and everything, that they basically are finding that they're using AI to modify images.
Yeah, this is an example.
No, to fake them.
Yeah, so this is what it is. The GAN is used to fake the images. So basically the output that you get here from the network is the output which is not from the training data. So it is considered the fake data, but what we use that for as a ground truth data. Yeah, so this is the architecture that we use.
No, they're actually putting fake data into the images.
Okay.
So the images are not accurate.
For nefarious purposes.
Yes.
Yeah, unbiasing. Yeah, we do that for testing our prediction results. Is that what you want to ask me?
Yeah, it seems like AI is doing it very successfully. We have great difficulty finding the bad data.
Okay, I'm not sure if I'm understanding your question, but sorry. If you want to answer, Josh, or ask if.
I think he's talking about deep fakes. And
Okay.
So
Is it for remote
what
sensing?
applications there would be here, because we're generally using satellite like raw feeds basically, right? So you can tune in with your own antenna to the satellite. Someone would have to intercept that stream,
Yeah.
fake that, and then rebroadcast it. That would be pretty tough. I mean, not outside their own possibility, obviously.
And there's a lot that they're trying to figure out how to deal with it because the computer, the data crunching to find this stuff, and they're finding it. You basically go, you're going down this road, and the road just ends, or that ship or that thing was supposed to be there. Well, it's not there. The bridge isn't there anymore.
Yeah, I reckon there's probably plenty of state actors interested in removing new missile sites and stuff in their imagery. Luckily, we haven't announced that. So.
Well, then they were putting new stuff.
Yeah, sure.
You get there and go, oh, you drove into a river. Well, we can't do that. Other questions for this?
Yeah, just.
Could you just explain the semantic labeling component of the research? I wasn't really clear about that.
Semantic labeling is the first step that we do in any part that I'm going to do it.
Explain that for everybody. Some people might not.
Yeah. So we do semantic labeling using the same network that we we use for the natural scenes. So it's not different for the remote sensing or the natural scene, but we basically extract the pixel wise. We do. Yeah, we do pixel-wise classification considering the global information in the image and not just labeling class to each object, but also considering the global information. What if it's a road? Do we really see a road next to the beach at all? If yes, then it's a road. If not, so we need to extract the meaningful information from different objects. We need to understand the spatial relationship, context relationship between different objects to say that we have semantically labeled that object, and just not classify that as road because the system understand that it is road, but it could be a missed pixel or it could be a noise in the image, making machine to understand it's a road. So it's just that giving a second layer of intelligence to the system to understand what the image looks like. So I'm not sure if I have time, but so even here it has predicted that it is the semantic segmentation for this image, but it's not the direct translation between satellite image to the segmented label, but it has also understand whether all these roads really exist or not, whether the pixels that is labeled as a road are really not a road or not. So if you see here in the true mask also you don't see this road, but it has given this road because it understands that if it starts road here and if there is some pixel that is labeled as road, it has to be a road on the whole stretch. And that is the advantage. Yeah, and that's the advantage of the prediction or the neural networks, which is better than the.
Are you running that against a database of known pixels?
Yes, we have to. Yeah.
That's been pre-generated.
And if you see here, also it is not batch level classifications. It is actually pixel wise classification. So not this area is not. Depending on the resolution, but this area is not completely classified as say buildings, but each pixel and each edges are considered here to go to a level like this at the largest.
Thank you.
All right, thanks so much.
Thanks.
I think so. Just gonna get this thing. Get out of here.
Next speaker is Devin Gatos, a Ph.D. student in forestry and environmental resources, and I'm Brett Hudson.
All right, thanks for that introduction. So today I'm going to be talking about the work that I'm doing, working with Oregon stakeholders to model a forest disease. But first I want to start off with a little bit of introduction because even though I've been hanging around the center for a while, it's not a given that everyone knows who I am or what I do. So my background's actually in biology and ecology, and I found that in particular I really like doing ecological field studies. There's just something really nice about being away from people, out in nature, studying how things fit together, and I found that I really gravitated towards that. So I was really excited when I got the opportunity to come to the center to study the ecology of sudden oak death disease. Sudden oak death is an invasive forest pathogen which to date has killed roughly 50 million trees along the Pacific coast. It's caused by a fungal organism that gets into the bark of the tree, causing these oozing sores that you see here. And these can rapidly lead to very widespread mortality, which then of course causes other environmental problems like increased wildfire hazard, habitat loss, things like that. In addition, it can be a big strain on the communities that rely on forest products, so these impacts also trickle into the social system. When I started here, my project was more of a traditional landscape, ecology, epidemiology type of focus. But the more that I learned about sudden oak death and all of its impacts, the more I wanted my work to be actionable. I really wanted to help do something about that. And in order to do that, I had to get out of the field and I had to start working with people. So I started talking to a lot of land managers out there to see what could be done about the issue. And I quickly found out that there's a lot of motivation to do management in Southwest Oregon right now. So this area is facing a new challenge because a new, more aggressive strain of this pathogen was recently introduced there, and it seems to be spreading faster and causing more damage. One of the major concerns here is that if the disease manages to spread northward into the neighboring county, a large shipping port could fall under international quarantine regulations. Since this port ships almost exclusively timber, there's a very real chance that this entire port could shut down, which would have pretty dramatic consequences for the economy of the region. One of the major issues that they have is trying to figure out where to manage. So they have limited resources, and not all disease locations can be treated in any given year. So how do you strategically use the resources that you do have to control that northward disease spread? And I want to stress, this isn't just a problem for Oregon. This is true of most invasive pests and pathogens, and frankly, a lot of other large-scale ecologic management kind of issues. Geospatial simulations of disease, like the one seen here, can be really useful for testing out different management scenarios. Essentially, they provide a risk-free environment where you can run a whole suite of different management options and see what your range of potential outcomes may be. But there were some challenges to applying these models to Oregon, not the least of all that they didn't exist for Oregon. They had been developed for California, and while there's a lot of similarities between the two systems, there's also some really key differences. One of which you can see here, is that the forest types aren't the same. They may have some of the same species, but the composition itself can be quite different. Another big thing is that California doesn't currently have that new strain of the pathogen that Oregon does, so we can't use that model to account for this new strain. Another big thing here is that we found these models aren't being used by stakeholders for policy and management all that often. I did a literature review looking at these kinds of disease simulation models and found that, especially in plant diseases, stakeholders aren't using them. This is probably a number of reasons. It's likely that people just don't know that these kinds of things are out there. But even when they do, these models can be complicated to use. For anyone who is in the class that I taught recently, sometimes it's even hard to download these models. And it takes a lot of coding and geospatial expertise to use them, which is a major barrier. So we have two main objectives here. We want to redesign this model to fit these Oregon conditions, and we want to make it more user-friendly for the people who are actually doing the management out there. And we thought a really good way to tackle both of these issues simultaneously would be to use a participatory modeling approach. So if you were here for Yelena's talk, you already know a little bit about participatory modeling and what some of the potential benefits there are. In this case, we really wanted to get that feedback on how to update the model and this tangible landscape system to make it more usable for this case. We also wanted to get people out there interested in how they could take this model and apply it to policy and management. And I think that this ended up being pretty beneficial. They gave us a lot of really great feedback, which then ended up sparking interesting research projects around the center. So one of the first things that stakeholders noticed was that the host maps we were using just weren't that accurate. They had been developed in 2012, and they were a fairly coarse spatial resolution. So this helped spark some of Nick Kruiskamp's work, looking at machine learning algorithms and remote sensing data to improve these host distribution maps, which will be helpful both for this system and other systems as well. Another thing was that the tangible landscape system, at the time, we were only able to manage that first year of a disease simulation, whereas land managers would realistically come in, manage every single year. So Anna Petrosova has been doing a lot of really great work on how to include this adaptive management and that computational steering into this system, which same with Nick's work, this will both help this case study and other case studies as well. And then lastly, the big thing is to update this model for Oregon. So we've made a lot of good progress on this lately, but we're facing some really tough challenges here, mainly because the disease system in Oregon is so much more complex than in California. In California, when the disease was first introduced, people didn't really know all that much about it, so there wasn't a whole intensive state-led management operation. But that's not the case in Oregon. They did intensive management throughout the disease, which makes it hard to find areas of natural spread that we can then go ahead and train our models with. But out of this problem, we're developing new ways to account for both the disease spread and the management together. And Chris Jones and I have been working on new ways to calibrate and validate these complicated spread models which I think is a promising approach not only for these pest and pathogen models, but also for land change models and things like that as well. So I definitely think we got a lot of really good feedback from our stakeholders. But what about our other goal of generating interest on their end? Well, I think that there's been some positive indications there too. Ever since the workshop, Oregon Department of Forestry has been really interested in using these disease models to project disease into the future and use that as part of an economic analysis, which then they can use to apply for funding and other things. We even got a shout out about this project recently in the Oregon legislature, which I think is pretty cool. So I think that while this project is ongoing, we've already seen some positive indications that working with stakeholders can be beneficial with these types of pest and pathogen models, especially in that it can spark new avenues of research and it can spark new ideas for management and planning with the stakeholders. So with that, thank you. Got some questions? Yes.
Is this similar to the issues they're having in Europe?
Yes, Phytophthora ramorum. Yeah, so Phytophthora ramorum is actually a global problem, and it's recently been introduced to France. Is that correct?
There's something like all over.
Oh, that's different. That's Xylella. Yeah.
There's different ones.
It's affecting birch and yeah. So I think we're actually talking about two separate things. So there is Phytophthora ramorum in Europe, and it's causing a big problem for the larch plantations. There's also this other invasive pest, Xylella fastidiosa, and it's causing a really big problem with the olives in Italy, which everyone who loves olive oil knows that would be a big problem there. Those trees are very old, and the people there really, really like them. So there's this really interesting kind of controversy between the researchers and stakeholders there, which I'm keeping an eye on. The stakeholders there called the government because they thought the researchers had introduced the pathogen purposely, which I don't think they did, but they got their labs raided and stuff. It's been a really interesting news story to follow. Oops.
Thank you, Devin. And our final speaker for the day is Jason Matney, and he is co-advised by Dr. Stacy Montgomery and Dr. Stacy Nelson.
Thank you for that introduction, Ross. And inspired by Kellyn, I thought I would just give a quick background as well. Back in 2015, when Jordan Smith reached out to me, I was living in Brooklyn and working at a fine establishment called Calexico. I can make a mean mango salsa. It was a Mexican restaurant, and they make delicious food, so I definitely recommend checking that out. But from here, I've now come to the Center for Geospatial Analytics, and this is a talk called Geospatial Data Management Recommendations for Land Managers. And essentially this story begins in 2015 with a paper that Jordan Smith headed with Bill Slocum, Charlene Smith, and myself. It was called a Needs Assessment Process for Designing Geospatial Data Management Systems within federal agencies. And essentially the crux of this paper was that there was a needs assessment process that needed to be identified and that was intended to be implemented as a first step to designing or redesigning a geospatial data management system. As you can see here, it sort of worked on the problem definition and stakeholder representation, as well as the initial scoping when working with a particular resource group. And so what I was hired here to work on, was the actual implementation of this geospatial management solution following some deliberation, outcomes, and evaluation. So that's what I worked on with a particular group called the Rivers, Trails, and Conservation Assistance Program. And so the RTCA, what they are, I don't know if who's heard of the RTCA before? Yeah, Stacy has. She is my advisor. So what the RTCA is they're a group within the National Park Service. And if you're a community organization that's focused on, for instance, working on trails, getting kids from the city out into parks, or doing other sorts of things such as generating funding for different conservation initiatives, you can apply for funds from the NPS through the RTCA. So they're essentially an interface in that sense. And they do really great work, and I would definitely recommend supporting them in any way you can. But working with the RTCA, people like Jordan, people like Bill and Charlene Smith worked with different stakeholders like Bob Ratcliffe and Peter Bonsall here, asking them questions like what was the primary purpose of their program, and what are commonly asked questions or requested tasks as your program performed, right? So this is an initial scoping phase. And this was outlined in that paper. I would recommend checking it out if you'd like to do something similar with your organizations. But essentially what we want to do is this is a standardized approach to assessing the problems, and we wanted a standardized approach to implementing a solution. So this is what we did. Envisioned from that needs assessment, we actually deployed an entire system based on geospatial data being stored in an enterprise geodatabase. Because prior to my coming here, data was being stored in a tabular database. It was siloed. You'd have to reach out to a database administrator, and if you had an application, you had to fax it to that person, and then they may or may not, catalog it. So it was clearly inefficient, and it was not transparent. Well, using, SQL Server, a virtualized interface based here at NC State, using Arc Server, in which you push data up onto the internet into ArcGIS Online, we created a WebGIS system that actually accomplished this implementation system. And we feel like it offers a standardized solution. Now, not everybody can, spin up SQL Server, have a virtual interface in which all of your data is stored, and then you put ArcGIS Server onto that virtual interface. So we actually moved everything to the cloud, and I'll get to that in a second. But this is what it ended up looking like, right? 3 panels, a very simple geoportal. And this is supposed to be simple because RTCA staff have to interact with it every day. And you cannot assume any expertise, right, with the users here. So essentially what they're allowed to do is enter data, analyze data, and update that data using a tabular record called a milestone. So this is what the data entry form looks like. We sort of enter project names, have drop-down menus, and we're actually able to then spatially geolocate that project on a map. Now, take note, these are all represented as points. Now, that was obviously a drawback because we weren't able to represent polylines or polygons in this system, which we got feedback on saying, well, we would really like to do that. And we're saying, well, the geoform doesn't really allow us to do that. So we're sort of looking for solutions that allow, but you can't let anybody just draw a line over the map and put it in as being official, right? So we need some way of structuring that so that we can, authenticate any sort of lines or polygons that are being put into our geodatabase. The GIS interface here allows you to do things such as calculate density, choosing best facilities, and most importantly, what they asked for in that assessment phase was doing some demographic overlays. So you see here, Tucson Park Preservation Project. This is a real project. Please do not write any of this information down. But the average unemployment in the area is 17%. So you could see that would be a really important thing to know if you were looking at helping people out around the Tucson area, that they have very high unemployment. And you could see how then that would relate to what you can ask of people if you're trying to get them to help preserve this park in Tucson, Arizona. And then finally, this milestone manager application just allows you to add a milestone and add attachments so you can continually update what's happening on that project. If you want to, check where funds have been distributed or see what sort of results have been generated. So we actually want to officially evaluate based on staff use how this actually worked out. So we used Qualtrics and we performed a user experience survey. I definitely relied on Stacy Supak's expertise in terms of developing survey instruments. I don't know if you know this, but she is an expert in surveying. And I will note, though, that I put this together, and here are some of the results, is that agreement does not necessarily correspond with a positive outcome. And I would definitely do that differently. So, pro tip, if you want to do one of these Likert scale surveys, make sure that all of your questions, if they strongly agree or disagree, means the same thing, conveys the same sentiment. So, for instance, enjoying filling out a form online more than using a pen and paper, 93% of our respondents at least somewhat agreed with that sentiment. So that's a good thing. They like doing things online more than pen and pencil. About half, though, found it difficult to use the features in a data entry form, and only 23% found that their attachments loaded correctly. So there was an issue with our secured sockets, or I'm sorry, secured credentials is what it was. Using HTTPS, we had some attachment fails, but we were able to resolve that by pushing everything up into the cloud. So what I would recommend is if you were to reproduce this, you do things in ArcGIS Online, because that system has matured greatly since 2015 when I began. And I know I'm out of time here, but this has been approved by the National Park Service and allowed us to transition and hand off our work to the NPS. So through an organizational handoff, essentially. So this is the paper, and again, shout out Stacey Supak. She definitely, she came in at the end and helped, what's the word? Just shepherd this into a publication that was definitely useful. So the implementation and evaluation of a geospatial management solution is out in the Journal of Park and Recreation Administration. I'd recommend you all check it out. And I'm out of time, but if you want to read the conclusion, that drives home exactly what we're trying to do here. So thank you for your time, and I'm happy to take any questions. Yes?
So have you resolved the line issue yet, or still in progress there?
So the question was, have we resolved the polyline issue? What we're actually doing right now is there's another PhD student who's implementing this standardized approach, but I do not believe they're using lines in that approach. So the answer is no. What we have to do, I think, is just make a custom web template, I think would be the solution, where you could draw it in and then it could be checked in some sort of version control framework, so to see whether or not it was accurate. And I don't know if there's funding for that, but that would be a really interesting project, I think, for anybody who's a first-year PhD student. Yes?
So it seems like pushing to the cloud was a major change that you made, but is there something else that you would have done differently from the get-go, if you've been known, or you know?
Absolutely. Yes, there's a lot I would have done differently from the get-go. Mainly, I think ArcGIS Server, I didn't anticipate there being sort of a resource problem with pushing information up through server, through a virtual interface. We actually had first push things out into two different virtual interfaces, and in order to slow down load times, or speed up load times rather. And so that was one thing. Really, I would have just gone with ArcGIS Online hosted feature layers initially from the outset. And I realized it wasn't mature in 2015 necessarily, but there was still the option to do that, and I think I would have taken that route initially. Yes, Bill.
Yeah, just to follow up with that, one of the reasons we went with the hosted environment was the software, the enterprise software was a little bit on the immature side when you started to deploy the secure sockets with HTTPS, when you also tried to lock down the back end of the database so people couldn't come in through REST services through the internet and lock that down. We had to deploy some of those techniques, and that is what shut down the server instance that would not accept some of these documents that people wanted to upload. And that's also what caused some failures on the system. And those were actually reported as bugs within the software in which people worked on. That's another reason we went to the cloud. We just ran into implementation issues with the software architecture.
And with that, I think we're out of time. So thank you, and I can hand it off to Byron, I believe, who has a note for you.
Oh yeah, we'll be all doing that. We just have it for, I guess, just the after hours hangout. If my colleagues are up for it, I think it's on us this time. So.